Today my class is the on the subject of Mohr circle. This is the question number 3, and this is the overhang crank. Overhang crank having two overhang crank pin, which is diameter is D. Now we find out the diameter of the D when applying the force P at 2 kN from the distance of the right side flat surface, from the distance of 50 millimeter, applying the force P, and this portion is inside of the hole where the rotating part which will rotate. Therefore, when applying the force P, then it will be the neutral axis. Suppose it will the neutral axis, then it will goes to rotate at a radius of 500 millimeter, and it will develop the torque. Now, it will first movement of the torque moment, torsion moment, and if this portion is applied, suppose this here, this portion is applied, suppose P is torque is applying here, then suppose P is here, then what happen? This part is inside of the hole, suppose, and it is static force, then it will be close to this axis. Then the force is applicable to P is here, this is 2 kN. First, this is the torsional movement, i.e. torsion force, and if this is in a straight portion, then another portion is the bending force. Suppose torsion force is not here, then the force is directly applicable to this axis. Meaning is this, that this pin is connected to this portion, and this part is static nature, and the force is applicable here. Then the bending moment is like the bending of the part. Our part is supposed to bend downward. Therefore, here two works are there. First works is the turning moment is applied, and second works is bending moment is applied. Therefore, when applying the force at a distance of 500 millimeter, there or finding out the diameter of the pin D, then we calculate torsional shear stress, I like it, shear stress of applying the torsion, and bending moment also applying the load P, and after that we apply the maximum shear stress theory, tau maximum equal to sigma B by 2 whole square plus tau whole square. Ultimately, we apply this formula and we calculate the first step. Here given the material is made of the 30C8. This is the, suppose the carbon steel material 30C8, and given the yield strength of tensile yield strength SYT, YT is the tensile yield strength, which value is 400 Newton per millimeter square, and given the factor of safety is 2, and the tau level, this is the permissible shear stress, this value tau maximum. Permissible shear stress is 0.5 SYT divided Fs. We know that the maximum shear stress theory, the tensile yield strength is half of the shear strength is half of the tensile strength yield strength, and divided by factor of safety, and we got the result of 400 200, and factor of safety is 1, then we got the result of 100 Newton per millimeter square for the tau level. At a consideration of the section XX, then that consideration, what is the diameter of the D, therefore we consider dxx is equal to what. Now consider the maximum shear stress theory, and this formula is applicable at the end of the question. Now calculating the torsional force, applying the torsional force and calculating the shear stress. Then the step 2, shear stress, we find out shear stress. Then first, here the torque is applicable at a radius of 500 mm. This axis to this axis is the dimension is 500 mm. 500 mm. Therefore, the R equal to 500 mm, which is applicable at the center of this. And now the load is applied, P equal to 2 kN. Therefore, P equal to 2 kN, I 2 into 10 to the power cube Newton. Applying the torque, mt equal to force into radius. Suppose a shaft is here, then this force is applied here, P, and this is perpendicular distance R, then the mt yard T, torque, equal to P into R, load into perpendicular distance, this is the radius. Then the P into R equal to 2 into 10 to the power cube into R, 500 mm. Now the value is torque mt equal to 1 into 10 to the power 6 Newton millimeter. If we calculate the value in Newton millimeter, then all the values we can change the millimeter to millimeter. Otherwise, your question will wrong. Now, applying the torsion formula, then torque T by IP, this is J. Some book follow the J and some book follow the IP. Then the T by IP, Fs by R, G theta by L. Here tau is the Fs, shear stress. Then we calculated tau. Then what? Then the cross multiplication, T into R equal to IP into Fs. Therefore, Fs equal to tau equal to torque T into R here and IP J here. We know that the J equal to pi by 32 d to the power 4. This is the polar moment of inertia for a circular beam. This type of beam is like, this is the shaft. Then the polar moment of inertia, then this is Z, IZ. IXX, IYY, and this is IZ. Then this known as the J equal to polar moment of inertia IP. Polar moment of inertia, this value is pi by 32 d to the power 4, putting here. And ultimately we get the result tau equal to 16 mt torque divide pi dq. And putting the values of the mt, which is 1 into 10 to the power 6, then the tau shear stress equal to 5.093 10 to the power 6 divide d cube Newton per millimeter square. This the stress is measured in millimeter square, and we take equation first. Go to the step 3. We can find out the bending stress sigma b. Suppose a bar where one section IXS is fixed and the load P is applying here, which is the 2 kN. Then for the, when here load is applying, then it will bend downward, I like. And the length is the total force is applicable as along the axis of this, along the axis of the pin circle. First the length is 100 mm, second length is thickness 25 mm, and third length is 50 mm, where the right side portion to the point of the action of force. Then P is here, and about section XX, the 175 mm length P is applicable. Therefore, making a couple due to the bending, then P into 1 175 millimeter. Therefore, the bending moment MB due to bending equal to 3.5 into 10 to the power 5 Newton millimeter. Now applying the bending formula MB by I sigma B by Y, we got here sigma B. Then MB into I by I. We know that the I by Y is the section modulus. Then I by Y pi beta 62 d to the power 4 divided d by 2. Y is the half of the diameter. Then IZ. Here I by Y is the IZ. This is the section modulus. Pi by 32 d to the power cube written here, and 32 is going up. Therefore 32 into MB 3.5 10 to the power 5 divide pi into d cube. Ultimately we got the bending stress equal to 3.565 into 10 to the power 6 divide d cube Newton per millimeter square. And this equation we take second equation. We calculate the shear stress is 5.093 multiply 10 to the power 6 d cube, and bending stress is this. Here on the perpendicular axis for shear stresses or load on the stresses on the x direction and y direction, and both two dimensional perpendicular stresses are showing here, and the shear stresses on this area tau xy and tau yx, which is the tau, this value. Here the bending stress is applied. Due to the bending stress, this is along the sigma x, this value is sigma x, this is here, and here sigma y is not working. Therefore sigma y is second perpendicular axis stresses were not working here. Therefore sigma y is 0. Now the sigma x, therefore sigma y is 0. We cut the sigma y and we put the value of sigma x instead of sigma b instead of sigma x. Therefore sigma b by 2 whole square plus tau square, and this value is I am starting question. This tau maximum is sigma b by 2 whole square plus tau whole square. This value is here. We put the sigma b bending stress and shear stress, and we got the tau maximum 5.396 into 10 to the power 6 10 to the power cube after mathematical calculation, and we consider the equation third. The tau maximum by applying the 0.5 SYT divide Fs, which is value is 2, and we got the value of 100 Newton per millimeter square. This value is equal to this value. Then 100 millimeter square is putting this equation. Therefore 100 equal to 5.396 10 to the power 6 divide d. Therefore d cube equal to, cutting the 100 at the right hand side, the value is 5.396 into 10 to the power 4 millimeter cube. Then diameter of the pin d equal to root under 3 under root cube root, this 5.396 10 to the power 4. This is in millimeter. Now calculating this formula in root under 3 5.396 10 to the power 4 equal to 37.79. 37.79. The diameter of the pin diameter of the pin D pin at section XX is 37.79 millimeter, and for sustaining the load of the 2 kilonewton about the 50 millimeter from the right hand side of the pin, and this cross section is at XX, then diameter D we can take 40 millimeter. For applying the all forces along the 40 millimeter diameter of the overhang crank pin, it will sustaining the load. Thank you.